Neuromorphic Computing. Here is your same structured beginner-friendly content for Neuromorphic Computing, Beginner Level, Introduction. Neuromorphic computing is an AI approach that mimics how the human brain works, using specialized hardware and algorithms. Traditional computers process data in a linear way, but the brain works differently. Parallel processing, event-driven signals, energy efficient. Neuromorphic systems try to replicate this using artificial neurons, synapses, spiking signals. They are used in robotics, edge AI devices, real-time systems, brain-inspired AI. Examples include smart sensors that process data locally, energy-efficient AI chips, robots that react instantly, brain-like learning systems. This topic helps beginners understand how AI can become more like the human brain. What is neuromorphic computing? Neuromorphic computing is the design of computer systems inspired by the structure and function of the brain. In simple words, neuromorphic, computing like a brain. Key idea. Instead of X, traditional step-by-step computing. Neuromorphic systems. Check. Process in parallel. Check. Use spikes, signals. Adapt and learn. Use less energy. Basic components. Component purpose. Neurons process signals. Synapses connect neurons. Spikes, event-based signals. Learning, rules adjust connections. Hardware, brain-inspired chips. Example of neuron concept. Input signal equals 5. If input signal equals 3, print neuron fires. Example of synapse weight equals 2, signal equals 3. Output equals weight times signal print output. Simple neuromorphic example. Python. Threshold equals 5, input value equals 7. If input value greater threshold, print spike generated. How neuromorphic computing works. Step 1. Receive input signal. Input signal equals 4. Step 2. Process in neuron. If input signal greater than 3, print neuron activated. Step 3. Send spike. Print spike transmitted. Step 4. Update synapse. Weight equals 2. Weight plus equals 1. Weight. Step 5. Learn from experience. Print. Learning completed. Spiking neural networks. SNNs. Neuromorphic systems use spiking neurons. Signal equals 10. If signal greater than 8, print spike fired. AI in edge devices. Runs efficiently on small devices. Device equals sensor. Print processing locally. AI in robotics. Fast reaction systems. Obstacle equals true. If obstacle, print react instantly. AI in real-time systems. Event-driven processing. Event equals motion detected. If event, print immediate response. Neuromorphic versus traditional computing. Feature. Neuromorphic computing, traditional computing. Processing. Parallel, sequential. Energy usage, low, high. Speed, fast, event-driven. Moderate. Architecture, brain-inspired, CPU, GPU-based. Full menu-based. Neuromorphic example, def, neuron fire. Equals, int input, enter signal. If value greater than 5, print neuron fired. Else, print no spike. Def, update weight. Weight is int input. Enter weight, weight plus or minus 1. Print updated weight. Def, detect event. Event equals input, enter event. If event, print event detected. While true, print 1, neuron fire. Print 2, update weight. Print 3, detect event. Choice equals input, enter choice. If choice equals 1, neuron fire. Elif choice equals 2, update weight. Elif choice equals 3, detect event. Elif choice equals 4, break, else print invalid choice. Color. Brain-inspired computing. Spiking neural networks. Event-driven processing. Energy-efficient AI. Parallel processing. Real-time AI systems. Real-life analogy. Neuromorphic computing is like the human brain. Neurons send signals. Signals trigger actions. Learning happens continuously. Ways to improve a project. Use neuromorphic frameworks. Brian 2, Nengo. Simulate spiking neural networks. Use real sensor data. Build robotics applications. Explore neuromorphic hardware. Optimize energy usage. Study brain-inspired algorithms. Use event-driven systems. Common mistakes beginners make. Treating it like traditional neural networks. Ignoring spike-based processing. Oversimplifying neuron behavior. Not understanding timing. Ignoring hardware differences. Where it is used. Robotics, edge AI devices, IoT systems, smart sensors, autonomous systems, healthcare devices, research labs, brain-computer interfaces. Large systems may include neuromorphic chips, spiking neural networks, real-time AI systems, edge AI platforms. Simple definition: neuromorphic computing. A brain-inspired computing approach using neurons and spikes to process information efficiently. Final summary: neuromorphic computing enables AI systems to mimic the brain, process data efficiently, react in real time, use less energy. It is a key step toward next-generation AI systems.